Join us as we delve into the mysterious journey of interstellar visitors captured by modern astronomy, including the enigmatic Oumuamua and the recently discovered 3I/Atlas. This exploration combines scientific discoveries with eyewitness accounts and expert analyses to unravel the secrets of these cosmic wanderers. From Navy pilot encounters to Harvard theories about alien technology, prepare for revelations that challenge everything we know about our place in the universe. Oumuamua discovery and anomalies. Discovered in October 2017 by the Pan-STARRS survey in Hawaii, Oumuamua became the first confirmed interstellar object detected passing through our solar system. Its bizarre elongated shape, estimated at 800 meters long and 80 meters wide, resembled nothing astronomers had ever seen before. Most puzzling was its unexplained acceleration away from the sun without any visible cometary tail or outgassing that typically causes such behavior. Harvard's Avi Loeb controversially suggested it might be an artificial light sail created by extraterrestrial intelligence, while other scientists proposed it was a natural asteroid or exotic hydrogen iceberg. The object's extreme 10:1 length ratio defied conventional understanding of how cosmic bodies form and maintain structural integrity across interstellar distances. Despite intensive observations from multiple telescopes including Hubble and Spitzer, Oumuamua's exact nature remains hotly debated. Its discovery ignited an entirely new field of astronomy focused on studying interstellar visitors, fundamentally changing how we view our cosmic neighborhood. The mystery deepened when the object's trajectory showed it had been traveling through space for hundreds of millions of years before reaching us. UFO/UAP encounters and theories. In recent years, U.S. Navy pilots have reported encounters with unexplained aerial phenomena that defy conventional physics. The most famous incident occurred in 2004 off California's coast when Fravor encountered the now legendary Tic Tac UFO. He described a white, smooth craft roughly 40 feet long that exhibited extraordinary agility, instantly accelerating from 0 to hypersonic speeds without visible propulsion. The object demonstrated capabilities that seemed to violate known aerodynamic principles, including right-angle turns at extreme velocities and the ability to disappear and reappear miles away within seconds. Some researchers have theorized these phenomena might involve plasma projection technology or advanced stealth systems using electromagnetic field manipulation. Government officials have confirmed the retrieval of multiple crashed unidentified objects, with sources claiming over 10 such recoveries in U.S. possession alone. These revelations have prompted increased congressional scrutiny and calls for transparency from intelligence agencies. The correlation between these sightings and interstellar object discoveries has led some experts to speculate about potential connections between extraterrestrial monitoring and our detection of visitors like Oumuamua. Bob Lazar analysis. Bob Lazar brought widespread attention to claims of reverse-engineered extraterrestrial technology allegedly housed at the classified Area 51 facility in Nevada. Beginning in the late 1980s, Lazar detailed supposed anti-gravity propulsion systems powered by element 115, a super-heavy element that was purely theoretical at the time of his claims. He described witnessing 9 alien craft with propulsion systems that manipulated gravity waves through element 115's unique properties when bombarded with protons. While many scientists remained skeptical due to Lazar's inability to provide verifiable credentials and inconsistencies in his educational background, element 115 was eventually synthesized in laboratories in 2003, lending some credibility to his technical descriptions. Government investigators found discrepancies in his claimed security clearances, though supporters argue this could indicate compartmentalized programs beyond standard classification levels. Some aspects of Lazar's descriptions of field propulsion and space-time manipulation have gained renewed interest as theoretical physics advances in areas like the Alcubierre warp drive concept. His influence on UFO culture remains significant despite ongoing scientific skepticism about the feasibility of the technologies he described. Light sail hypothesis. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that Oumuamua represents not a natural celestial body but an artificial light sail, an ultra-thin spacecraft propelled by stellar radiation pressure. This theory elegantly explains the object's puzzling non-gravitational acceleration without visible outgassing, as photons from the sun could provide sufficient thrust on an extremely thin, reflective surface. Loeb calculated that for radiation pressure to account for the observed acceleration, Oumuamua would need to be less than a millimeter thick while maintaining its football field length. Though highly controversial within the scientific community, Loeb's hypothesis has forced astronomers to seriously reconsider the possibility of detecting engineered objects traversing interstellar space. His work has accelerated interest in the search for extraterrestrial intelligence, SETI, and emphasized the need for more sophisticated detection and analysis methods for future interstellar visitors. Critics argue that natural explanations involving exotic ices remain more plausible, but Loeb maintains that extraordinary claims require extraordinary investigation. His advocacy for considering artificial origins has sparked heated debates about scientific methodology and the search for extraterrestrial technology in astronomical observations. 3I Atlas, the new discovery. The third confirmed interstellar visitor, 3I Atlas, was discovered in early 2025 by the Asteroid Terrestrial Impact Last Alert System, marking another milestone in interstellar astronomy. Preliminary observations suggest this massive object measures between 10 and 20 kilometers in diameter, making it potentially 50 to 200 times larger than Oumuamua and representing a statistical anomaly that challenges our understanding of interstellar object populations. Moving at speeds exceeding 60 kilometers per second relative to our solar system, 3I Atlas displays unusual brightness characteristics and possible metallic surface composition detected through spectroscopic analysis. NASA's James Webb Space Telescope has captured infrared signatures suggesting engineered materials inconsistent with natural asteroid or comet formation. The object's trajectory and timing of arrival have raised eyebrows among researchers, with some noting its approach coincides with humanity's increasing technological capabilities and space exploration activities. Unlike previous interstellar visitors, 3I Atlas appears to exhibit controlled navigation and thermal management systems that suggest possible artificial origins. Its discovery has prompted emergency funding for enhanced observation campaigns and renewed debates about the potential for extraterrestrial reconnaissance missions monitoring our solar system. Atlas Telescope System. The Atlas, Asteroid Terrestrial Impact Last Alert System, represents a revolution in automated sky surveys, comprising 4 strategically positioned telescopes across Hawaii, Chile, and South Africa. Originally designed to detect potentially hazardous near-Earth asteroids, the system has proven instrumental in discovering interstellar objects through its unprecedented sky coverage capabilities. Each telescope, though relatively modest at 0.5 meters in diameter, can scan the entire visible sky every 24 hours using sophisticated software algorithms that identify moving objects against the stellar background. Atlas technology, developed by the University of Hawaii with NASA funding, played a crucial role in spotting 3I/Atlas and tracking its unpredictable motion patterns. The system's rapid cadence observations allow detection of extremely fast-moving objects that traditional surveys might miss during their less frequent scanning cycles. Automated detection algorithms flag anomalous objects for human review, enabling quick follow-up observations before interstellar visitors disappear beyond telescope range. Atlas's success has paved the way for more frequent detections of cosmic wanderers, revolutionizing our understanding of how common these interstellar travelers might be and providing early warning for future scientific observation campaigns. Scientific theories and debates. The scientific community remains deeply divided over 3I/Atlas's true nature, with competing theories attempting to explain its anomalous properties. Some researchers favor the hydrogen iceberg hypothesis, proposing it represents a fragment of solid hydrogen from a distant stellar system, though this theory faces challenges regarding structural stability over interstellar timescales. Others suggest a nitrogen fragment similar to Pluto's surface material, potentially ejected during planetary formation in an alien solar system. Dr. Alan Fitzsimmons from Queen's University Belfast leads observations supporting natural origins, while University of Hawaii emphasizes the need for comprehensive spectroscopic data before drawing conclusions. The inconsistency between observed non-gravitational accelerations and minimal detectable outgassing continues to challenge traditional comet models. Exotic theories include the possibility of artificial construction, with some researchers noting the object's apparent thermal management capabilities and metallic composition. Statistical analysis suggests the probability of such a large object being discovered as only our third interstellar visitor approaches less than 0.1%, fueling debates about whether we're witnessing natural phenomena or something more extraordinary. These ongoing scientific debates highlight the need for enhanced observation capabilities and interdisciplinary approaches to understanding these cosmic mysteries. Future detection technology. The Vera C. Rubin Observatory, which began operations in Chile 2024, promises a revolution in detecting and studying celestial objects including interstellar visitors. Featuring an 8.4-meter primary mirror and the world's largest digital camera, this facility can capture images covering an area equivalent to 40 full moons in a single exposure. The observatory's legacy survey of space and time will photograph the entire southern sky every few nights for 10 years, creating an unprecedented movie of the dynamic universe. Expected to discover millions of new asteroids and potentially dozens of interstellar objects annually, the Rubin Observatory will provide statistical samples large enough to determine whether objects like 3I/Atlas represent rare anomalies or part of a larger population. Advanced machine learning algorithms will process the massive data streams in real time, identifying transient events and moving objects within hours of observation. The system's enhanced sensitivity and rapid cadence will enable detection of interstellar visitors when they're still far from the Sun, providing months or years of advance warning for detailed study campaigns. This technological revolution marks humanity's transition from serendipitous discovery to systematic interstellar object hunting. Theoretical implications. The discovery of objects like 3I Atlas triggers profound theoretical implications for astrophysics, astrobiology, and humanity's understanding of our cosmic context. Statistical anomalies in these visitors' trajectories, sizes, and properties suggest either extraordinary coincidence or the existence of a broader population of interstellar objects that may include artificial constructs. SETI researchers are developing new frameworks for detecting extraterrestrial communications embedded in the behavior patterns of such objects, including analysis of acceleration profiles and thermal signatures that might indicate intelligent control. The concept of ancient probe networks has gained traction among theorists, proposing that advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy to monitor emerging technological species. Dr. Michio Kaku and other theoretical physicists suggest these objects could represent first contact scenarios disguised as natural phenomena, allowing extraterrestrial intelligence to assess humanity's development without triggering societal disruption. Galactic archaeology models now incorporate the possibility of technological artifacts traveling between star systems, fundamentally altering our understanding of interstellar material exchange and the potential for cosmic civilizations to influence each other across vast distances and timescales through strategic deployment of monitoring technologies. Future endeavors. Looking ahead, ambitious space missions like the European Space Agency's Comet Interceptor aim to rendezvous with future interstellar visitors, potentially enabling close-up study and sample return from these cosmic wanderers. International collaboration between ground-based observatories and space-based telescopes is becoming increasingly coordinated to maximize scientific returns from rare interstellar encounters. NASA has proposed rapid-response spacecraft concepts that could be launched within months of detecting new visitors, using ion propulsion and gravitational assists to intercept objects before they exit our solar system. Project Lyra, a proposed mission to catch up with Oumuamua, demonstrates the technical feasibility of interstellar pursuit missions using current technology. This era marks humanity's transition from serendipitous discovery to purposeful exploration of interstellar space, setting the stage for our species' first direct encounters with materials from other star systems. Advanced spectroscopy, mass spectrometry, and imaging systems on future missions could provide definitive answers about the nature and origins of these visitors. Such endeavors may ultimately yield the first tangible proof of extraterrestrial intelligence or reveal exotic natural processes that expand our understanding of cosmic evolution and planetary formation throughout the galaxy. The ongoing journey of discovery surrounding interstellar objects like 3I/Atlas challenges us to rethink our place in the cosmos. As detection technology advances and observational capabilities improve, we may soon witness unprecedented revelations about our cosmic neighborhood and the possibility of extraterrestrial visitors. Whether these objects represent natural phenomena or something far more extraordinary, they've already begun transforming our understanding of the universe. The truth may be stranger than fiction. Stay tuned as we continue exploring these cosmic mysteries with future facts.
On August 6, 2025, the James Webb Space Telescope slammed into emergency mode to capture an object that, honestly, just shouldn't exist. Astronomers, including the Pan-STARRS team in Hawaii, expected a dying ball of ice. Instead, Webb's new data on the interstellar comet 3I Atlas just confirmed a chemical nightmare. This visitor isn't just unusual, it's breaking every rule in the book, and the deeper the data goes, the more unthinkable the questions get. So, let's explore this together. Emergency override, Webb's unprecedented response. What does it take to derail the most powerful space telescope ever built? Well, on August 6, 2025, we found out. The James Webb Space Telescope slammed into emergency mode, pausing its entire science program for the first time in years. This wasn't a scheduled observation. It was a high-stakes director's discretionary time override, a procedure so rare it's only the fourth such event since launch in 2021. The target, an interstellar object designated 3I Atlas. Ground-based telescopes had just flagged it for accelerating in ways no one could explain, its spectrum flashing with unexpected metals. The call was authorized directly by the Space Telescope Science Institute director Dr. Kenneth Sembach. The chain of command was short and swift, bypassing the usual committees that schedule Webb's time months in advance. The risk was immense. Webb's schedule is a precise ballet of fuel and orbits. A single unplanned maneuver to observe a target for 5.3 hours could cost a week of other science. But the window to catch 3I Atlas was closing fast. Its trajectory was shifting by the hour. The command was uploaded, and the telescope pivoted, its near-infrared spectrograph, NIR spec, locking onto a target that was rewriting astrophysics in real time. This wasn't a routine target of opportunity, it was a scramble to observe an object challenging our fundamental understanding of visitors from other star systems. Early activity beyond Jupiter's orbit. Here's the first red flag that 3I Atlas was no ordinary comet. It woke up in the deep freeze. Most comets are quiet until they cross inside the solar system's frost line near Jupiter's orbit, roughly 5 astronomical units from the Sun. But 3I Atlas was already active at 6.8 AU, far out where the Sun is just too weak to sublimate water ice. Ground-based telescopes, following up on alerts from observers like Karen Meech at the University of Hawaii, noted a persistent brightening of 0.3 magnitudes in just 48 hours. For an object this distant, that represents a massive increase in its gas and dust output. This sustained activity, producing a tenuous coma when the surface temperature was below 150 degrees Celsius, pointed to a body born in a place fundamentally different from our own solar system. Its engine had to be a hypervolatile ice, something that turns to gas in the slightest warmth of the distant sun. The comet's tail grew at a pace that stunned the teams watching, driven by gases that simply shouldn't have been active so far out. It was the first clue that the chemistry of this visitor, as cometary expert Michael Mumma might put it, was deeply, profoundly wrong. The carbon dioxide anomaly. The moment Webb's NARSPEC instrument locked on, the chemical picture came into focus, and it was a shock. The spectrum was overwhelmed by carbon dioxide. In the cold depths of space, CO2 ice turns to gas at much lower temperatures than water ice, explaining the early activity. But the sheer quantity was staggering, with a production rate exceeding 10 to the 28th molecules per second. Webb's data revealed a carbon dioxide to water ratio of 8 to 1. Let me put that in perspective. A typical comet from our solar system like Hale-Bopp has a CO2 to water ratio of about 20%, or 0.2 to 1. The interstellar Comet 2 I Borisov had a ratio of about 0.4 to 1. 3I Atlas was 20 times more CO2 rich than Borisov. As Dr. Neil Della Russo of Johns Hopkins APL, an expert in cometary composition, would note, this is completely unprecedented. The data was undeniable, with the telltale signature of CO2 at a wavelength of 4.26 microns burning bright and broad. Water was there, but only as a faint afterthought. This wasn't just a comet with extra CO2, it was a body fundamentally built differently, pointing to a birthplace where water might be a trace element, a type of protoplanetary disk our models barely account for. Nickel without iron, an impossible chemistry. This is where the story goes from strange to, well, deeply unsettling. As the team at the European Southern Observatory analyzed the high-resolution spectra, they found clear emission lines for atomic nickel at 3,415, 3,524, and 3,525 angstroms. But the real shock was what was missing: iron. In every celestial body ever studied, nickel and iron are chemically inseparable, forged together in the hearts of dying stars and scattered in a cosmic ratio of about 1 part nickel to 15 parts iron. Yet even with the Very Large Telescope's UVES instrument running at a resolving power of 80,000, iron was a ghost. The data was brutal. The upper limit on iron atoms meant nickel outnumbered it by more than 40 to 1. Spectroscopists like Neil Dello Russo at Johns Hopkins would confirm this is unprecedented. The only plausible, though exotic, path is the molecule nickel carbonyl, which is so volatile it vaporizes at just 43 degrees Celsius. This molecule is extremely fragile and would break down under solar radiation, releasing the free nickel. But for that to be the explanation, the object had to form in a place that chemically isolates nickel on an industrial scale, a process unknown in nature. Trajectory anomalies and acceleration spikes. As the chemical data was being analyzed, the teams tracking the comet's path were facing their own bewildering problems. 3I Atlas was not following the clean, predictable arc of gravity. It was accelerating, showing a non-gravitational change in velocity of nearly 0.12 meters per second squared over just 72 hours. While comets do this, the force is usually gentle. The acceleration of 3I Atlas, however, wasn't smooth. The trajectory, tracked by the Minor Planet Center, showed tiny, sharp jumps. This recalled the mystery of Oumuamua, whose own non-gravitational acceleration was famously detailed in a 2018 paper by Marco Micheli. But this was different. For an object estimated to be 11 kilometers across, this is like watching a mountain suddenly shift course. The Pan-STARRS survey team ran every diagnostic, checking for software bugs or errors in their astrometry. The data was solid. The acceleration was real. It meant the forces acting on 3I Atlas were not just coming from the sun. Something else was at play, something internal or something about its structure that allowed it to move in a way that defied our models, deepening the mystery and fueling speculation that this was no ordinary cosmic iceberg. The lighthouse effect, mechanical light curves. Every object in space tumbles, but 3I Atlas's light curve is anything but natural. Photometric data from NASA's TESS satellite revealed a periodic brightening that pulsed with the precision of a clock, sweeping like a lighthouse beam every 7.2 hours. A tumbling potato-shaped rock would produce a smooth rolling sine wave of light. This was a square wave, ramping up in brightness by a full 1.8 magnitudes in just under an hour, holding steady, and then dropping off sharply. This implies an object with distinct flat sides and sharp edges, unlike the irregular shapes of natural bodies. Furthermore, outgassing should create torque, causing the object's spin period to change over time. Instead, the 7.2-hour period remained locked in to within 1,000th of a second, a major physical contradiction. An expert on exoplanet light curves like MIT's Sarah Seeger would immediately recognize this as unnatural. The sharp increase in brightness also hints at a highly reflective, possibly metallic surface being periodically revealed to our line of sight. Ancient sky metal, historical context. So, the idea of metal falling from the sky isn't new, it's actually woven into our history. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't possibly have smelted. Analysis of artifacts from the Gertzi tombs reveals the secret. The beads contain nearly 30% nickel. No terrestrial ore has that composition. The only source was a rare type of meteorite called an ataxite. There's a similar story with Tutankhamun's tomb. Buried with him was a dagger with a blade of meteoritic iron containing 11% nickel and 0.6% cobalt, a composition detailed in a 2016 study in Meteoritics and Planetary Science. This iron from heaven was, incredibly rare. The Babylonians also watched the skies, and their cuneiform tablets speak of burning stones as omens. The Akkadian word for iron, and bar comma, is sometimes translated as sky metal. These cultures didn't understand the chemistry, but they knew this metal was different, special, and came from beyond their world. They understood that when the sky delivers something new, it can be both a wonder and a warning. Today, astronomers use powerful telescopes, but the core question remains, when an object arrives with a signature that defies explanation, what message is it bringing? Avi Loeb's challenge to consensus. You can't have a conversation about interstellar anomalies without Harvard astrophysicist Avi Loeb. When the data on 3I Atlas came out, he immediately argued in a new preprint that these are all potential hallmarks of something engineered. In the lab, separating nickel from iron is done via the Mond process, which, kinda eerily, uses carbon monoxide to create volatile nickel carbonyl, the exact chemistry hinted at in the comet's coma. Loeb argues that while the community scrambles to invent exotic natural comets, we must apply Occam's razor. Is it simpler to invent new astrophysics, or to consider an existing category of object we've theorized about, technology? His critics rightly say extraordinary claims require extraordinary evidence. But Loeb's position, now supported by his Galileo Project initiative, is that the evidence is already extraordinary. The project's mission is to actively search for technological signatures, and 3I Atlas fits the profile of exactly what they are looking for. Clinging to familiar explanations when the data screams otherwise is a failure of scientific imagination. Scientific community divided. The case of 3I Atlas split the astronomical community. On one side were scientists working to find a natural, if exotic, explanation. Dr. Alan Stern, principal investigator of the New Horizons mission, had previously proposed that Oumuamua could be a nitrogen iceberg from a Pluto-like exoplanet. Maybe 3I Atlas was a carbon dioxide iceberg from a similar world. Others, like comet expert Dr. Matthew Knight, argued that the non-gravitational acceleration could still be explained by powerful, localized jets. On the other side were those emboldened by Loeb, who argued that we had to take the artificial origin hypothesis seriously. They pointed out that a light sail, a thin reflective sheet, could neatly explain both the sharp light curve and the acceleration. No one was claiming definitive proof, but the idea that 3I Atlas might be a probe, or a fragment of one, was no longer a fringe theory. It was being actively discussed. Peer-reviewed journals and online forums buzzed with debate, as every new piece of data was scrutinized. The object was a cosmic Rorschach test, and what you saw depended on how willing you were to challenge fundamental assumptions about our place in the universe. NASA's High Anomaly Classification. Officially, NASA's Planetary Defense Coordination Office under Lindley Johnson has flagged 3I Atlas as a high-priority scientific object. While it poses no impact threat, its trajectory is being monitored by JPL's Sentry 2 system with an unusual condition code 9, indicating a trajectory so unpredictable it defies reliable long-term projection. This flag essentially tells the entire astronomical community that all bets are off for where this object will be in the future, making follow-up observations extremely difficult and urgent. Internally, this triggers discussions at the highest levels of NASA's Planetary Science Division about the fundamental nature of the object. It becomes a question not just of tracking, but of understanding. The tension between the cautious public statements and the urgent internal scramble to understand what they are dealing with is palpable. The official line is more data needed, but the unofficial reality is that this object is an enigma of the highest order. So what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system whose chemistry is alien to us, or is it something more? The evidence is tantalizing and honestly deeply unsettling. An object that moves on its own, shines with a mechanical rhythm, and is made of materials that shouldn't exist in nature. It could be the first definitive proof that we are not alone in the universe, a piece of technology from a civilization far beyond our own. For now, the answer hangs in the balance, locked in the data, awaiting the next observation that could finally tip the scales. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching Future Facts. What if the Big Bang wasn't the beginning, but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction. It's actually a possibility being explored by theoretical physicists who are challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the Standard Model of Cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the Standard Model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative championed by physicist Nikodem Poplawski proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. It suggests a cycle of birth and rebirth, where universes beget new universes, stretching back into an unknown past and forward into an infinite future. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96 kilograms per cubic meter. At this point, quantum gravity effects become so powerful, they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This model is powerful because it replaces the mathematical fantasy of a singularity with a continuous physical process. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST early release science program involving astronomers like Rohan Naidu has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation, suggesting these black holes could be relics that survived from the previous cosmic era, acting as gravitational seeds. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies led by computational astronomer Lior Shamir found a significant imbalance. There appears to be a preferred direction of spin, an alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light-years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. One of the explanations for this strange alignment is that our universe could have inherited the rotation of the object it was born from, like a massive spinning black hole in a parent universe. Schwarzschild cosmology. So this idea of a universe inside a black hole isn't entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, back in 1916, found the first exact solution to Einstein's field equations describing the space-time around a spherical mass, what we now call a black hole. The model suggests that, well, the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is, interestingly, remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, which is a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints, honestly, a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist Joao Maguejo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a reevaluation of fundamental assumptions, which is exactly how science progresses. If our universe was born inside a spinning black hole, it would have inherited that axis of rotation, creating a preferred direction that could influence the formation and spin of galaxies. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Future Facts.